Dear students, welcome to another day's lecture in Elements of Machine Design. Yesterday we started a new topic, design of springs. So in that we have seen um, different types of springs and a little bit about terminology and other things. You see, now if you say classification of springs, springs can be classified as helical springs, conical or volute springs, torsional springs, disc or bevel springs, and leaf springs. Okay, so under the helical springs, there can be helical compression spring and helical tension spring. Under the helical compression springs, it can be closed coil helical spring, open coil helical spring. We'll see what is closed coil and what is open coil. Okay, then, under the torsion springs, there are further classification: helical torsional spring, helical torsional spring, and spiral torsional spring. So this is how classification is there. You know, where when somebody asks you in the exam or something, you will be able to write this chart. Tension helical spring. It has coils close to each other. This is the tension helical spring. And the tensile load is applied to the ends. You see, here and here the load F, that is tensile load, is applied. Okay, and then this type of spring is used for spring balances, spring loaded safety valve, and other things. Okay, this is the normally what we will come across is the helical compression spring. Okay, and then there can be closed coil. And now the difference between closed coil and open coil. Closed coil helical spring and say, yeah, you see here closed coil helical spring is there. In a closed coil helical spring, the helix angle is very small. Helix angle means what? The alpha that is shown here. You see, as in the case of threads, we were having helix angle. Here also we are having helix angle. See, now this is the particular the axis of the spring coil, and this is the line perpendicular, but these coils are at an angle. Okay, so this angle that is making, if this is what they are saying, if this is less than 10 degrees, then it is called closed coil helical spring. If it is more than 10 degrees, then it is called as open coil helical spring. So in closed coil helical spring, the helix angle is very small, less than 10 degrees. The coils are so close that there is a very small gap between the coils. Say in that case, the coils are very close, they are saying, and the angle is, you see, you remember this closed coil helical spring has less than 10 degrees. Okay, whereas open coil has more than helical springs. Okay, and the gap will be more. But here in this picture, nothing like that gap is not visible. Maybe this is not the correct picture of representing it. Okay, anyway, so that is the difference between closed coil and helical coil springs, and this value of 10 degrees for the helix angle you remember. Okay, and then conical springs, which is in the form of a cone, and in the volute springs in the form of paraboloid. Okay, these are the two things we have seen. Where in case of helical springs, the spring stiffness is constant. Here the spring stiffness increases with the load. The spring stiffness increases with the load in those two cases. Okay, and then we have torsional springs. Torsional springs, this is the spiral shape. You see, remember, you see, this is the helical shape and this is the spiral shape. If something is like this, we call it a spiral. If something is like this, we call it a helical. So torsional spring, so this is the spiral spring, and this is a spiral torsional spring. In torsional springs, there can be of helical or spiral. This is helical, this is front view to side view, and this is the one view only. This is for the spiral spring. So it is made up winding of flat strips in the form of spiral. The major stresses induced are tensile and compressive due to bending of strips. You see here, in this case anyway, we are not going to design this, but you know, if somebody asks you what type of stresses are induced in case of in the flat strips, as you can say, the tensile and compressive stresses are being induced. This type of string is used in wristwatches. Wristwatches means, you know, the watches that we are wearing on the hand, and pressure gauges, etc. Torsional helical springs are made by winding a wire like compression spring, and the force is applied tangentially. There, they see this force here no is applied axially, whereas here the force is applied is tangentially. So when these are used in clutches. Today we are going to ask one quiz question. Torsional helical spring. Which is the spring that is used in the clutch at a torsion helical spring? Okay, there are used in clutch lever of automobiles and door hinges, etc. Ah, so here axial, in case of helical compression spring it is axial load. Here in helical torsion spring it is the tangential force. Okay. Then another type is Belleville spring. Belleville springs are made up of cone disc. These are all cones. You see, this disc, upper disc is a cone. Then this is another cone. It is like a frustum of a cone. The stresses are induced are tensile and compressive nature. The desired load deflection characteristics can be obtained by using number of cone discs. You see, number of cone discs, the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 cone discs are here. Okay, anyway, so like that, this Belleville spring. See, only for information's sake, what is the Belleville spring you are learning? No numericals will be asked in Belleville springs. Okay, and then about the materials we have already seen, and now let us come to what are the stresses in the springs. In the stresses in the springs, uh, sorry, 1 minute. Yeah, in the type of springs, another spring was there, that is leaf spring. About yesterday, I showed you the pictures also, Google pictures. Okay, and this has you know, this is the top one. You know, this is I see the leaf springs are made up of number of semi-elliptical flat plates called leaves. These are held together by center bolt. You see, this is the center bolt, and provided with rebound clips at intermediate positions. These are rebound clips, this one at intermediate positions. It is commonly used in suspension. The top one, no, which is the full length, this is called master leaf, and the others are called as graduated leaves. Okay, and then we have seen about the terminology that is used, and this terminology is only for helical compression spring. So because why are we learning only this because you know, this is easy to understand, and once you know the basics of springs, then you can extrapolate it to other springs also whenever necessary. So at this stage we are learning only the basic things. So we have seen the solid length means if a compression spring is there like this. Compression spring means that spring which can be compressed is a compression spring. जो दबता है उसको compression spring बोलते हैं, जो दब नहीं सकता है और जो खींचा जाता है उसको टेंशन स्प्रिंग बोलते हैं. वेरी सिंपल है ना. ये जो कंप्रेशन स्प्रिंग है, ये ये जो है ना, कुछ लोड आया, थोड़ा दब गया, तो ये जो है ना, ये सॉलिड लेंथ नहीं हुआ. मगर जब ये कॉयल एक के ऊपर एक टच करता है तब वो सॉलिड लेंथ होता है. सॉलिड लेंथ का फार्मूला अपन कल भी देखे हैं, LS is equal to N dash D. Okay, like that. And then the free length means when there is no load at all. For that also we have seen a formula. Free length is solid length plus maximum compression plus clearance between the adjacent coils. Say maximum compression को अपन delta maximum लेते हैं, तो clearance between the adjacent coils इसको 0.15 delta maximum ऐसे लेते हैं. ये कल देखे थे अपन. So another formula is length of the what is that, free length. Free length is N dash D plus delta max plus N dash minus 1 into 1. N dash minus 1 means this is the number of gaps. N dash is the total number of coils, and 1, if you are subtracting 1, means that is the number of gaps between. Okay, gap will be 1 less. Okay. Okay. And then we have seen about the spring index. Spring index is mean diameter of the coil upon the wire diameter, dm upon d. As I said, this will not have any units because numerator and denominator both are having units as millimeters. They'll get cut, and what is remaining is a dimensionless quantity, that is the spring index. Then we saw about the spring stiffness. Spring stiffness also is called a spring constant, and it is given by small k. I don't know, here they have written capital K, but normally I think it is given small k. Small k is load upon deflection, and that means 1 मिलीमीटर दबने के लिए कितना लोड लगता है, कितने न्यूटन्स लगते हैं, तो उसको स्प्रिंग स्टिफनेस बोलते हैं. तो अगर 1 मिलीमीटर दबाने के लिए 100 न्यूटन्स लग रहे हैं, तो स्प्रिंग स्टिफनेस जो होता है 100 newtons per millimeter, like that it will be. Then we have seen about the pitch. Pitch is the free length upon the number of gaps. Number of gaps is n dash minus 1. Okay, free length okay, otherwise it can be given by this formula also, lf minus ls upon n dash plus 1 plus d, sorry. Okay, then these are the desirable properties of the materials with which the springs are made. Springs are made, it should have high resilience, it should have high ductility, it should be ductile. Okay, it should have high static strength, it should have high fatigue strength, and it should have creep resistance, and it should be non-corrosive. Okay, these are the desirable properties of the materials. Okay, and yesterday we have seen some of the names of the materials also. Now today we are not going to see it. Now let us see about the stresses in springs. What are the stresses that are coming upon? Okay, you see here there is a picture shown. Figure 5.5.1 shows a free body diagram of a portion of the spring. I will show you in a minute that picture, that figure. Subject to the axial force F. The axial force F induced in the stressor induces the stresses at each and every section of the spring wire having diameter d. While resisting the axial force, the spring wire is subjected to these two things. One is twisting moment, capital T, about its own axis, induced torsional. It induces torsional shear stress. So this twisting moment induces torsional shear stress tau. Okay, then direct shear stress. There is, see, one is torsional shear stress, another is direct shear stress. So this direct shear stress is due to the axial load that is coming. That axial load is F. Okay, now I'll show you the figure. Yeah, this is the free body diagram. This is the free body diagram. This one is the free body diagram that we are talking about. So you see, this is the spring, this is the axial force, and we have cut it and shown here. So when we cut it, there is, because of this axial force on this section here, cut section, there is a force F acting, which is turning to directly shear it. Okay, and then because of the same thing, there is a twisting moment, capital T, which is trying to turn it like this. Okay, so these are the two things. Because of F, there is a direct shear, that means it is directly going to induce a cut in the spring at that section. And because of this torque T, which is in terms because of F, there is a torsional shear stress tau induced. So there are two stresses induced. One is direct shear, another is torsional shear. These are the two stresses that are coming. So see, we can say you see, the stresses induced in the spring will be the tau r. R means, you can say, the resultant stress. Resultant stress induced can be written as tau t, because of that the torsion, and tau d because of the direct shear. Direct shear means transverse shear, and this is torsional shear. Okay, these are the two stresses that are coming upon this section. which is shown by the free body diagram. Okay, now we have to derive a formula for it. Now when we are deriving a formula, you see, uh, now you see torque can be given by F into the distance at which this force is acting. F is the actual force and distance at which it is acting is the radius. Radius is nothing but mean diameter by 2. That means F into R is F into D by 2. You see, now we'll not be solving all this using radius. Now we use diameter only because handling the diameters is easy. Okay, anyway, from the torsion equation we have torsion equation. From that you can get this relationship for the uh, shear stress. Shear stress is equal to torque into radius upon the polar moment of inertia J. Okay, now from this, now what we can do is let us substitute. Okay, and also one more equation we were having because of the torsional shear. You see, actually, you see here, no, you see, um, what we should say here, if we substitute, what is J? J is pi by pi d to the power 4 by 32. Okay, and what is R? D by 2. Okay, so if we substitute all that, what you will get is, see, this is the torsion equation we get. You see, this we have derived in the springs also, in the shafts also. Shaft is capital T is pi by 16 tau d cube. That is the same formula here. The same formula we will you substitute it and see, you should get this value. Okay, now torque, see, from here we have torque is equal to F into dm by 2. So replace T by F into dm by 2 here. See, there are two D's. One is capital D, one is small d. Capital D is the coil diameter and D is the d is the wire diameter. So here D by 2 is there. This 2 will cut to a 16 and 8 will be remaining, and this can be substituted. You will arrive at this equation. This equation is tau is equal to this is the torsional shear. Torsional shear stress is equal to 8F dm upon pi d cube. Okay, this is one equation. Okay, and direct shear is simple. Direct shear is load upon area. Load is F, area is pi by 4 d square. So you will get 4F into 4F divided by pi d square. So the resultant shear stress is equal to uh, tau plus tau t plus tau d. Okay, plus or minus, because in one direction it will be plus, another direction it will be minus. So you will have this equation, resultant stress. Okay, see here they are saying positive at the inner edge, negative at the outer edge of the wire. Okay, and now what let us see, we have to design for the maximum torque only, so minus we neglect and we take only positive. Okay, so now from this 8F dm upon pi d cube you can take out, and what is remaining is 1 plus small d upon 2 capital D. Okay, see, small d upon capital D, you see, there is something called as spring index. Spring index is capital dm by small d. So if you replace that by C, so and half is replacing it by 0.5, so you will get this equation. So resultant torque is equal to 8F capital dm upon pi small d cube bracket 1 plus 0.5 by C. Okay, this is one equation you are getting. Okay, uh, and okay, so that thing that is in the bracket here, that this thing you replace by a constant value Ks. Now Ks is shear stress correction factor. So we can say now shear stress tau, total resultant shear stress tau, is equal to So shear stress tau is equal to shear stress factor, correct, shear stress correction factor, it is shear stress correction factor into 8 f dm upon pi dq. Okay. And this shear stress factor, shear stress correction factor, is used to account for the direct shear stress and effect due to torsion. Only these two it is considering. Okay, one is direct shear, another is torsional shear. Okay, so see that this equation shows that the effect of direct shear becomes more pronounced when the spring index C becomes smaller. The smaller the value of C becomes, the smaller value the C, if you reduce this, then this becomes more, this becomes more. That's what we are saying. That means for smaller coil diameters of the spring, see, direct shear will be more. From where are we getting this? From this equation A. Yeah, because this factor, this side factor, no, this factor is because of the torsional shear, this factor is because of the direct shear. In the direct shear only value of C is there. In this there is no value of C. So if this is becoming more, ultimately shear stress is going to become more. So this has no effect. Torsional shear stress is not affected by the spring index. Only direct shear stress is affected by the affected by the spring index. Okay, so this also is a question for quiz. You can ask, see what happens if this is if spring index C increases. Okay, spring index increases means only the direct shear will become more prominent, means will become more. Okay, now here, this is the wire means the small, this one. Okay, this wire. Okay, in that, we can plot various types of stresses. We are having one direct shear. Direct shear is simply, it is throughout, it is like a rectangle. Rectangular representation of the direct shear, and torsional shear is 0 at the center, and towards the radius it keeps increasing. Okay, in one direction one sign, another direction another sign. One side if you take negative, the other side it will become positive. And if you to superimpose these two, that means if you combine these two, then this is the resultant. Okay, so this is, you see, towards this side, if you see, if you are going, one is going down, one is going up, means one is positive, one is negative, so this will result less. Whereas this side both are in one direction, the same direction, positive direction. So both are positive means, the resultant will be more positive. So there will be more shear stress towards this. Here less shear stress, here more shear stress. So because of that, when we are designing, we'll be designing at this place. Okay, where did they say? See, positive at the inner edge. See, this is the inner edge, this is the outer edge. Now you say, you take this circle to be here. Okay, this is the inner edge, this is the outer edge. So more curvature, more torsional, more torsional as well as direct shear will be at the inner edge, not at the outer edge. That means cracks initiate means, what, it will not cut at the outside and propagate inside, it will cut at the inside and propagate outside. That is the meaning. Okay, then there is something called as Wall's correction factor. Okay, Mr. Wall has designed it, so that is why his name Wall, capital W, Wall, WAHL, Wall. Okay, this is one of the very important question. No, so many times in the short theory questions it is asked. So what is it? Let us see. See, actually, now till now, what we have considered for the stress, for this stress, we have considered only factor Ks, and we call that factor shear stress correction factor. In this shear stress correction factor, this value is this. Okay, in this, but in this thing, what stresses till now we have considered? We have considered only the direct shear as well as the torsional shear. Nothing else we considered. But this man, wall's correction factor or stress factor, Kw, it is given as, is the modification factor of Ks. So this man has corrected, Professor A.M. Wall has conducted many, many experiments, many researches he has conducted in this, and he first determined more accurate way of finding out the resultant shear stress induced in the spring wire analytically. The curvature of the wire increases the shear stress on the inner surface of the spring, and it decreases it slightly on the outer side. Just now we have seen that the inner side there is more stress, outer side lesser stress. This curvature effect, stress is localized and is significant only when the fatigue load is present. When the fatigue load is present, fatigue loading means what? A kind of cyclic loading. Like a sinusoidal load. Up, it goes positive, negative, so like that. Okay, for static load, this stress can be negative. Okay, in order to consider the effect of both direct shear stress and curvature effect, now he's talking about something else, curvature effect. The shear stress factor Ks is replaced by another factor Kw. This Kw is known as Wall's shear stress factor and is given by this formula. You see this formula, you remember, this is an important form relation for Kw. Kw is, K is capital here and W is small as this suffix. Okay, this is 4C minus 1 upon 4C minus 4 plus 0.615 upon C. Just you remember this. Okay, you see the first term, this term gives the correction for curvature effect, and the second term gives correction for direct shear stress factor. This is the direct shear and this is curvature effect. Okay, curvature effect because of the shear stress. Okay, this is more accurate. You see, this is a earlier what we came across, this one shear stress correction factor. So they analytically they have done it, and maybe this man also here it said analytically he may have done some experiments also. I say here also it is said analytically here, but I may have done some experiments also, because of which he arrived at this thing. Cap 4C minus 1 upon 4C minus 4 plus 0.615 C. This is the Wall's correction factor, all Wall's shear stress factor. That's how it is. Okay, you remember this thing. Okay, and you remember that this first factor is because of the curvature effect and the second factor is because of the direct shear stress. Okay, so therefore now our formula here, what we derived here, this one, this is the resultant shear stress formula. Now Ks should be replaced by Kw. Now forget about Ks. Hereafter we are not going to use Ks. We will be using Kw only. So tau shear stress is equal to Kw into 8Fdm upon pi d cube. This is an important relation that we are going to use in springs. You remember this formula. This is an important. This is one formula that is to be remembered. This is another. Unless they ask you to derive the relation, okay, sometimes they may ask you, or derive the equation for the resultant stress coming in the wire in the compression helical spring. Then you will have to do all this. Otherwise, finally what you have to remember is this formula and this formula and this formula, because now for finding out Kw you have to know this. You see, what is C? C is the spring index. You see here, C is the spring index. Now what are these different things? Okay, tau is the final resultant shear stress. Okay, Kw is the Wall's correction factor. 8 is a constant. F is the load that is coming upon the actual load that is coming upon the spring. Capital Dm is the mean diameter, pi is a constant, small d is the wire diameter. Now you know all these things, so you will be able to estimate what is the shear stress. You will be able to know what is the shear stress induced in the wire. Okay, now sometimes no, you may have to draw this graph also. What is this graph? Is a Wahl's correction factor only we are talking about. Is a this figure shows the effect of spring index. Spring index is taken on the x-axis, say starting from 0 to 1 2 3 4 5 6 7 up to 16 he is plotted. Okay, and Wahl's correction factor Kw is plotted on the y-axis. Y-axis, you know, 1, 1.2, 1.4, 1.6, 1. Up to 1.8. Okay, and now you see when the chart is plotted like this, that means what? See, if the value of the spring index C is more like 15 16, Wahl's correction factor is very less. It is just 1.2 1 point, not even 1.2, 1.12 1.14, like sorry, 1.0 to 1.04, like okay, that much only. But you know, spring index is reducing. As it is reducing, see now, some most of the times we'll be taking spring index 6 or something. So for spring index 6 means it is coming to maybe around 1.2 or something like that. 1 point, I think 1.2525 or something it comes. If C we take 6, no, I think it comes to 1.1212, 1.2525. Okay, so if you plot like this, it should come somewhere here. Okay, so like that. See, you need to remember how this curve is. See, at 1.8, no, it is around 1 or something. Okay, from there it is coming like this. So this is, see, on the x-axis we are taking spring index, on the y-axis we are taking Wahl's correction factor, and you know, as the spring index is increasing, the effect of Wahl's stress factor is very little. As the spring index is less, you know, is less and less, you know, the Wahl's correction factor becomes more prominent. Okay, so this is the thing. Now we have derived an equation for the shear stress that is induced in the wire. That is one formula, important formula that we use for design of compression helical springs. Now another formula we are going to devise now, and this correction factor, this is because of the deflection in helical springs. Okay, the deflection of the spring is due to the torsional moment T and a direct shear force F acting on the spring wire that we have discussed before. Okay, total active length of wire is equal to length of one coil into number of coils. See, total active length of the wire means what? Suppose this spring was not there, it is initially only a wire, a long straight wire. What is the length? That is L. So length of one coil is the circumference pi d. Okay, how many coils are there? N number of coils are there. So the length of the, with this length of the wire, you know, what spring you can make? You can make a spring of diameter dm and number of coils n. Okay, now let theta be the angular deflection of the wire when acted by the torque T. See, because of the torque T, some theta is being induced. Okay, this is the angular deflection. So the angular deflection is theta, whereas delta is the actual deflection. Actual deflection बोले तो ऊपर नीचे होने वाला deflection है, और थीटा जो है ना, ये ऐसा ट्विस्ट होने वाला डिफ्लेक्शन है. इसको इसलिए इसको एंगुलर डिफ्लेक्शन बोलते हैं और इसको एक्सियल डिफ्लेक्शन बोलते हैं. सो डेल्टा इज द एक्सियल डिफ्लेक्शन. डेल्टा इज एक्सियल डिफ्लेक्शन इज this theta into the radius. Radius is dm by 2. Okay, okay, now we also know from the torsion equation. See, this is the torsion equation. T upon j, ip also it is written sometimes. Okay, j, T upon j is tau upon r into g theta. L. This is the formula. Okay, this is the what formula? Torsional equation. You see these two equations you keep in mind always. You have learned it from strength of materials and applied mechanics. Okay, so you remember what two equations? One is torsion equation, another is bending equation. Both are similar. No, no, like this only. Okay, torsion equation is T upon J into is equal to tau upon r is equal to g theta by L. Now the first term and last term only let us consider like this, T upon J is equal to g theta by L. Now from this you can say theta is equal to T into L, you take L that side, divided by Jp into G. G is the modulus of rigidity. Okay. So, and this, IP is equal to pi by 32 to the power 4. You see, this IP बोले तो J. J का यूनिट्स हमेशा J का यूनिट्स हो, I का यूनिट्स हो, ये हमेशा यूनिट्स mm to the power 4 होते हैं. Okay. So, you see, the relation between theta and delta. Maybe this is delta. Okay. So this is theta and this is delta. Delta is equal to theta into dm by 2. Okay, like that he is given. Okay, now let us come here. Now substitute the value of L and J in equation C. Where is C? In equation B. You see, we have J value is this and we have L value this. L is this, no, and J is this, no. Here L and J means IP, L and IP values you put here. Okay, and what will become B will become like this. Theta is equal to this is a T value, and this is L value, and this is J value, and this is G. Okay, you substitute all these things. Not only L and TP, even T value, capital T also is substituted. So if you simplify this, you should get this value, this one. Okay, and now substituting theta in equation B. Equation A, sorry, it should not be B. See now theta, you see now delta is equal to theta into dm by 2, no. Here A, see they by mistake they have put B, it should be A. So now this theta value we got, this theta you substitute, you put here. So what will become this, the whole thing into dm by 2 is delta. Now delta, again you simplify it like this and you simplify it like this. Okay, you see now, here no, in terms of capital D and small d it is given. Here in terms of capital C and small d are given, because capital D m cube upon small d cube will become C cube. Okay, here it is written D C is nothing but dm by 2, small capital Dm by small d. Okay, so now the stiffness, now from this, now this is another equation. See, one equation we have seen, important equation for the springs is shear stress without Wahl's correction factor. Another equation is this, delta is equal to 8f dm cube on g to the power n into n. Okay, n also you put up, then it becomes 8f d cube n by g d to the power 4. This is the second most important, and when I'm saying important, you remember these are the two equations normally we are going to use. One is for shear stress using that Wahl's correction factor. Another is this delta. Okay, delta is 8f d cube n by g d to the power 4. Okay, Okay, this is a small relation that we can remember. Now the stiffness is F upon delta. Okay, and this is the value. Okay. Okay, today we'll stop here. Thank you.